All right, well, I'm going to get going. The goal today is to do the whole path integral quantization of general relativity, maybe in one day. And we've set ourselves up here. Basically, we're going to do three things. We're going to do background field. We're going to do gauge fixings and ghosts, like last time. And then we have to do the one loop divergences, which is basically heat kernel. Okay. So I actually think we'll just jump in. Let's not do any philosophy. Let's just jump in. I'm going to do background field. So I'm going to take G mu nu and break it up into a background field, G bar mu nu, plus kappa H mu nu, G upper is then G bar upper minus kappa H upper, and then the next term is kappa squared H mu lambda H lambda nu. Some intermediate steps, I'm going to drop kappa just because it messes up the formulas, but then it comes back when I do the Lagrangian. Okay, same old kappa as always. Yeah, it's kappa squared. So kappa is the same old lambda. Kappa squared is 32 pi g newton. Okay, and you'll see when I put it back in that it's been put in just the way that makes the Lagrangian for this H look like a normal kinetic energy piece. And that's what we did it when we did the weak field limit. It's basically the same thing. So a lot of the formulas are going to look the same as the ones where we did back then, where instead of G bar we had eta. Okay, so that's actually one of the beauties of what we're doing. Okay, so we need, at this stage, then we need to get gamma and curvatures, and there's a bunch of algebra associated with it. I'm not going to do all the algebra, but I want to do some of it because it actually highlights one of the key points. So let's work on gamma. The connection, we're going to really we'll write it in the following way. There's the first piece, which is just the connection with G bar. Then there'll be a first order piece, which is gamma mu nu beta, and I'll stick one bar under it. I'm following, okay, following Tufton-Veltman. And then there's gamma with two bars under it, which is a second order. This is order H. This is order H squared. Okay, actually, I did want to say something early on. The classic work on this is Tufton-Veltman. I have put it on the web page, so if you want to go read it, it's on the web page, and it's great work published in the Annals of the Institute of Henri Poincaré. It's a slightly hard to read by some of the conventions, but it's a great paper. You should look at it. Okay. Anyway, so let's go here. So just to remind you what gamma looks like, let's write out gamma bar. And so it's 1/2 G beta lambda. Let's see what notation do I want? Beta alpha. Then d mu G alpha plus d mu g nu alpha minus d alpha g mu nu. And since this is gamma bar, all those are the ones with the background field. Okay. Then the ones I'm going to work on is the first order term, gamma under bar mu nu beta. So looking above there, you can see there's two terms. There's one term where g bars turn into h's, and then the other term where the other g bars turn into h's. There's only two places g bars enter, so there's two places. So let's do this. It's 1/2 g bar beta alpha. Then the first order you get h nu alpha plus d nu h. I'm sorry. My mistake up here, I did two terms the same. It's supposed to be mu and nu interchanged. Let me correct that. All right, so then down here, it's d nu h mu alpha minus d alpha h mu nu. So that's the one correction, and the other one has the h in the first piece. So it's -1/2 h beta alpha, and then derivative of g bar. Okay, so there's two terms there. Now, the first term, okay, so what I'd like to do is look at that second term there and see that it sort of looks like gamma bar with the over bar. Okay, so for the guys that came in, what we're doing is we're doing background field method for quantizing gravity. And I'm working out one example, and then the rest I will give you without too much algebra. But it illustrates something useful. This guy almost looks like gamma over bar, the background field one. So let me try to make it look more so. I'm going to make it look like the following. It's 1/2. Let me pull a g bar beta alpha out in front. And then I have a big bracket here. The first piece I'm just copying over now is the derivatives on h. Okay, so that's just copied the h piece. But the second piece I'm now going to rewrite in a different form here. I'm going to have h with lower indices, so I'll put the alpha, tau, g bar, tau sigma. Okay. Okay, so what I raise and lower with g bars. So this combination here gives me h beta sigma upper from the two pieces there. And then I'm rewriting the next piece as d mu g nu sigma, the index from above, plus this symmetric piece minus d sigma g mu nu. Okay, so I hope you can see I've just rewritten that. Basically, I've got lower indices over here, but then I'm raising them with g bars, and I'm just rewriting the second term. Okay, the beauty of doing this is that this is 2 gamma bar mu nu tau. And this is starting to look almost like I could make it into covariant derivatives. Okay, I've got usual derivatives and I've got a connection piece. And so the move is to make this into covariant derivatives. So let's do this. It requires a little bit more. So I'm going to write this as 1/2 g bar beta alpha, big brackets. Okay, so I do d mu h mu alpha, and I'll take one of these guys and write minus gamma bar mu nu tau h tau alpha. Okay. Next line, I'm going to write the second piece, d nu h mu alpha, and then minus gamma bar tau mu nu h let's write it. Nu mu, I'm using that symmetric tau alpha. That's fine. Then I have the d alpha h mu nu. That's unpaired. And now let's add and subtract a couple things. If we do this cleverly, it's gamma bar alpha nu tau h tau mu minus the same thing, gamma bar h alpha nu tau h tau alpha. And I'm going to do it again with a different one, but it's basically mu nu interchanged. I have tau up here. I have mu alpha h tau nu minus the same thing. End bracket. Okay, little painful, but let's. So if I label this 1, 2, 3, 4, and I move them in the following locations. Let's see. 4 ends up being up here, plus 4. 2 ends up here. And there's a minus sign there, sorry. Plus 1 there and 3 here. Okay. Then you stare at those and you realize that this is, if I put those in the right locations, then the top line is the covariant derivative on H. So when you have a covariant derivative on a tensor with 2 indices, you have 2 gammas, and so there are the 2 gammas. And then this guy is a covariant derivative with mu nu interchanged. And this last one, these 2 guys here, enter there. Okay. So if I do that, gamma underbar mu nu, beta is 1/2 G bar beta alpha. And basically, I just get covariant derivatives instead of usual derivatives. So I get d bar, the derivative with respect to the background field, mu h nu alpha, d bar nu h mu alpha minus d bar alpha h mu nu. So the point of all that work was really to convince you that you get covariant derivatives with respect to the background field. Okay, that's the important thing. If I do gamma bar, it turns out to be almost, gamma double bar, the second order one. It's very similar. It's 1/2. It's h beta alpha, and then I do the d covariant derivatives. Okay, so again, after some algebra, it's basically the same thing. Psychologically, it's the same. You just add and subtract pieces to make those into covariant derivatives. This is one of the key features of the background field method, is that we end up with it being covariant with respect to the background field. So let's make the general statement here. Basically, what I'm going to look at is gauge invariance in the background field. Okay. So remember, gauge invariance in general is x prime mu is x mu plus some c mu of x. Dx mu is prime is dx mu plus d nu c mu dx nu, which we can write as delta mu nu plus d nu c mu dx nu. And this was, in our old notation, some lambda mu nu dx nu, which was a function of x. Okay, the transformation on G bar, on G as a whole, G mu nu of x goes to this lambda mu alpha G mu nu at x prime, lambda nu, actually, sorry, I got my indices wrong there. That's alpha and beta. Okay, and so if we're doing an this is at x prime, if we're doing an infinitesimal, I would say that this is G alpha beta at x prime. I'm then expanding the lambdas plus, plus G alpha nu d mu c alpha plus G mu alpha d nu c alpha. Okay, so what I've just done is I've expanded these guys here. And so I always have the G sitting down there, and it's either one side or the other. I've got either the mu side or the nu side gets expanded. But then I also have this guy here, and I would write that as G alpha beta of X plus C alpha, I'm Taylor expanding, D alpha G. Okay, sorry. Let me get my indices right. Screwed them up. That was mu nu. Okay, we had free indices mu and nu. Alpha and beta were summed over. So that still is mu nu there. And this is mu nu. Okay, so let me summarize that gauge transformation. So here's the gauge transformation, the infinitesimal gauge transformation. On G. G goes to G plus G nu alpha D nu C alpha plus G mu alpha D nu C alpha plus C alpha D alpha G mu nu. This, yes. Yeah. Let's get that one right. I think, so if that's nu, then this guy's mu. Let's get that right. Alpha nu D mu alpha. Okay, I think that looks right. All right. Now, let's just do the following. We can replace the derivative of mu's by covariant derivatives mu with respect to the background. Okay. So let's just take a look at all these terms here. I have G mu nu plus, well, I have G mu, it's alpha nu, and let's write this as covariant derivative. D mu C alpha plus gamma mu, let's do sigma alpha C sigma. Okay, so that's so by. Okay, yes. Can replace so what I'm doing here is I'm just rewriting this, all the partials is covariance, and then we'll take a look at it and see that the connection pieces all drop out. So that's the background there. Okay, then my next one was G mu alpha. I've got D nu C alpha plus gamma nu sigma alpha C sigma. And then I've got plus plus C alpha. Now, here's derivative on G mu nu, usual derivative on G mu nu. G mu nu. So now there's two connections that we have to do, and they're minus signs. So it's gamma bar alpha mu sigma sigma G mu sigma minus gamma alpha nu sigma G sigma nu. All right, there we go. Okay, so let's look at this guy here. I've got a G connected up with one of the mu nu indices. The other one gets another index, and the connection goes to the gauge variable, and then the upper index is contracted with the G index. Then you go over here and you get one of the same things. I've got, I guess it's this one here. The other index on the G is connected up to the upper index. The other index here on the connection gets connected up to the gauge parameter. Okay, so this guy right there and that guy right there cancel. This guy right there and that guy right there cancel. Okay, just by relabeling. It's alpha and sigma get relabeled. Okay, so gammas cancel. Okay, so this is, at this stage, I'm still general. I have G bar, G mu nu goes to G mu nu plus G mu alpha D bar. Well, I still haven't really said what D bar is yet, but let's just go with it. C alpha plus G alpha nu D bar mu C alpha plus C alpha D bar alpha G mu nu. Okay, at this stage I do background field. Did I have it wrong? Two nus, yes, alpha. One of them is an alpha. There we go, alpha, thank you. All right, so now we write G is G plus H, the G bar plus H. So we have G bar plus H mu nu, sorry. Going to this G bar plus H mu nu plus G bar mu alpha plus H mu alpha D bar nu C alpha plus, let's carry it out all the way to the end because there's one thing I need to say, plus H alpha nu D bar mu C alpha. The thing that I need to say is this last term only has an H in it. D bar alpha H mu nu. Okay, remember D bar covariant derivatives acting on G's with any indices. Alpha mu nu gives 0, so if it's a covariant derivative with respect to G bar, it gives 0. So this guy is only an H piece. Okay, at this stage, you can do one of two things. You can say, well, if H is neglected, I have the gauge invariance for G bar. That's fine. That's nothing new really. We knew that was true. But I could also say, let me assign this to H. Okay. So I'm going to assign it to H, and let's look at the leading piece. Let's H mu nu, then goes to H mu nu plus d bar nu c mu plus d bar mu c nu plus order H times c. I've done one thing in writing it this way. I've used so I have G bar. Let's take a look at this piece here. G bar mu alpha d nu c alpha. G bar mu alpha d bar nu c alpha. I can bring the G through because D doesn't act on it. So the D bar nu G bar mu alpha C alpha, and that just lowers the upper index. So the D bar nu C mu. Okay, these guys you can write out. It's okay. It still involve G bars and covariant derivatives, but this now tells me that the H interactions are covariant. They're themselves gauge interactions, but they're covariant with respect to the background field. Okay. This is a big deal because what it tells me is that H can be treated like a usual tensor, like a usual field. I can do whatever I want with the path integral, and I'm going to get results that are covariant with respect to the background field. So my answers are not going to lose the gauge invariance. Okay, so that's probably one of the biggest beauties of background field method path integral quantization is that you can keep track of the gauge invariance of the theory all the way throughout. And so what you'll see and you saw that up here, you basically saw that the expansion involved covariant derivatives, and we'll see it all the way throughout. And that then guarantees the gauge invariance of the final answer. Okay. All right. I don't want to do too much algebra, but I do want to talk through one thing here with the curvatures. Okay, so basically we're going to again do R mu nu alpha beta is R mu nu alpha beta upstairs with a bar over it, and then one with an underbar and one with a double underbar, which are of order h and h squared. I want to just only talk through it. So let's just write out the answer for what's R with one underbar, mu nu alpha beta. Well, it's the covariant derivative on the first order piece Okay, so remember the curvatures come as either derivatives of h or gamma squareds. And so what I basically do, there's a gamma squareds packaged into the d's. All the gamma squareds get packaged into the d bars, and this is in some sense what it has to be, a covariant first order expression involving 1. And if I do the second one, let's see, I'll do it schematically. You'll see what it means. So the second one, it's the derivatives on gammas with 2 bar, the second order ones, plus gamma. Let's not bother putting the indices on with 1. But this is actually not what we need. But we need the action as a function of h, not s as a function of gamma. So if you just contract this, there's still work to be done. So there's more work. Okay. And what are the interesting pieces of that work? Well, I did some of it. The things you need to use the d bar mu g alpha beta bar equals 0. And then the other thing you end up using is d bar mu d bar nu commutators h alpha beta is, now there's 2 terms in this. It's a curvature mu nu gamma beta h gamma alpha plus r mu nu alpha gamma h beta gamma. Okay, we haven't quite worked that out. We did when we did the commutator with, we acted on a vector with 1 index and it gave me 1 term. If you have this commutator of covariant derivatives acting on something with 2 indices, you get the two terms out. I don't know. That's the most unique new piece that you need in order to do this. But then after a lot of work, here's where you come down. Okay. So the Lagrangian is the square root of minus g minus 2 over kappa squared r, and now my kappas are back in. Okay. It starts off square root of minus g bar. Then minus 2 over kappa squared r bar. Then minus 1 over kappa. So now we've lost 1 power of kappa because it's really kappa h. I've got h alpha alpha r bar minus 2 r alpha nu h nu alpha r bar. Now comes the fun terms. So there's a 1/2 d bar alpha h mu nu d bar alpha h mu nu. So that looks like your usual kinetic energy pieces. There's a second piece which we've actually seen before, d bar alpha h lambda lambda d bar alpha h sigma sigma. So basically the trace. There's two more pieces plus d nu h lambda lambda d beta h nu beta minus d nu h alpha beta d alpha h nu beta. Okay, then minus some r bar terms. I'll just write them out quickly. It's a quarter h lambda lambda squared minus 1/2 h alpha beta h beta alpha h alpha nu r bar alpha nu plus 2 h nu beta h beta alpha r alpha nu. All the d's are with bars over them, and all the curvatures are with bars over them. Okay. So this form isn't all that interesting, except to note the two types of terms. There's the covariant derivatives on H. If you go back, when we did weak field limit, this is exactly what we had, but with usual derivatives going to covariant derivatives. Okay, and then we just picked up some background stuff, background fields that are, again, quadratic in H. Okay. So that's the background field expansion to there. The first term is, let's spread as 2 over kappa h alpha beta. It's r bar alpha beta minus 1/2 g alpha beta r bar. Okay, well, that looks like Einstein's equation. This, if was just pure gravity, we would set this to 0. If we're adding matter content, we would put minus kappa squared over 4 t mu nu there from the first order expansion of the matter part. But the feature that you know is that always the first order term vanishes because it's the equations of motion. So no matter how complicated your Lagrangian is, the first order term is going to vanish. No matter what we do, okay? The temptation could be to set r and r mu nu to equal to 0 at this stage, because in pure gravity, I'm just doing pure gravity at the moment, r alpha beta is 0, so I could just go up and set these up to 0 up there. But let's not do that, because we want to carry it along. We're going to add some other matter fields to the Lagrangians in the end. So let's just carry them along. There'll be a moment in the future, probably not today, but a moment in the future where I say, for pure gravity, I can set these equal to 0, but let's just carry them for now. Besides, that's what Tufts and Zaltzman did. Okay. All right, well, we're not quite out of the woods. We have to do gauge fixing. Gauge fixing, remember when we did weak field, we chose to set d mu h mu nu minus 1/2 d nu h lambda lambda equals to 0, and that was harmonic gauge. Okay, and when I did it, so this cleaned up the equation of motion. That was what I first did. You notice that turned the equations of motion into just a plain old D'Alembert, if you remember. We then went back and did the Lagrangian. I added a gauge fixing term. The gauge fixing term was the Lagrangian gauge fixing was 1/2 the gauge term here, h mu nu minus d nu h lambda lambda quantity squared. Okay, and that simplified the Lagrangian. The Lagrangian turned into, then it was just 1/2 d mu h d alpha h mu nu d alpha h mu nu minus 1/4 d alpha h d alpha h, that's the trace h sigma. And we had another piece here, which was, the matter piece, kappa over 2 h mu nu t mu nu. But this gave us our propagator in free space. So that was what we did before. Okay, so the goal here is basically the same thing. Though actually I should comment, this adding this gauge fixing term back before we did path integrals is a bit funny. I mean, you get used to it, but if you think about it, what you've done is you've changed your Lagrangian. I always have trouble explaining this the first time I do it before I do path integrals. You've changed your Lagrangian and removed the gauge symmetry in the Lagrangian by adding a new term to it. How do you know that doesn't screw up the whole theory and make it terrible? The only way you really know this is going through this path integral exercise that we did, where you add a constraint, which was just the identity, and you exponentiate a term, and so the tricks that we went through last time are the only way that you know that that's not going to screw up your theory. We get used to it, but the path integral is the way to do it. So let's do it again. I'll just go through it here. So now we want to do the same type of constraint. We want to have the constraint be some constraint that's called C mu, which is d nu h mu nu minus 1/2 d, this is d bars, of course, d bar mu h lambda lambda. So that's going to be my harmonic gauge constraint in the background field. Okay. We're going to add to the Lagrangian basically, which is some it's 1 is the, we're going to add the determinant, which I'll calculate in a minute, the determinant, which is the function of h. The delta function, that's the constraint c mu minus some f mu, a constant, to the Lagrangian. Then you exponentiate in the following way. We did this is what we did last thing. You write this as df delta c mu minus f mu of x e to the I integral d for x bar 1/2 f mu nu no f mu nu, sorry, just f mu, which turns this into e to the I integral d for x square root of minus g times the Lagrangian, the gauge fixing Lagrangian. Okay, so f is just the constraint squared, where there's a half. So the gauge fixing constraint then is just the covariant piece of what we did before. D bar mu h mu nu minus d bar nu h lambda lambda squared. Okay, so I could have just said that, but here we've gone through this pathway using the path integral to exponentiate this gauge fixing piece. Okay, then if you go up here, you can guess what the answer is going to be. I've added some of these new derivatives. They're just covariant derivatives, but I'm doing the same algebra as before, except instead of partial derivatives, I have covariant derivatives. So this simplifies the Lagrangian. L of gravity plus L gauge fixing is 1/2 d bar alpha h mu nu d bar alpha h mu nu minus 1/4 d bar alpha h lambda lambda d bar alpha h sigma sigma plus r terms. Okay. All right, so there. That's better in a way. I've fixed the gauge, I've simplified. Last thing to do here is ghosts. Any questions at this stage? Just the issues. Yeah. I have, let's see, I've got a free index new here. So it's new, and then I just sum. It's basically, it's 1/2 c mu, where c is that constraint. Okay. And I have to think a little bit whether it's plus or minus. Minus signs, it's a little bit of a pain to follow minus signs here, but all right. Now the ghost fields. The ghosts, of course, are always scary. So but it's actually not that hard. Our constraint, the gauge constraint, the c mu is d bar nu h mu nu minus 1/2 d nu h lambda lambda. Your instruction is to do a gauge change with respect to H, and the ghosts are related to the gauge change. So the gauge change is what we worked out before. H mu nu goes to H mu nu plus d nu C mu plus d mu C nu. And those are backgrounds. Everybody's backgrounding. So if you do that gauge change, you have to substitute this gauge change for H mu nu there, and the second one for H lambda lambda there. Okay, so let's just do it. Delta C mu, the piece that depends on the gauge change. Well, it's d bar nu, and there's two pieces. There's one with d bar nu itself, C mu plus d bar mu C nu. Then there's minus a half d bar nu, and then this guy gets traced. So there's two terms, both of which are d lambda c lambda. So there's two. Okay. Okay. Actually, for notational ease, let's actually, what have I screwed up? I've screwed up something. That's for notational ease, let's write this correctly. That was a mu. This is a mu. This is a summed index. And since some of my indices are nus, I'm going to make them nus. Okay, so just any old summed index. All right. Yeah. So this first piece is d bar nu d bar nu c mu. That's sort of box d squared. And then I get two pieces that actually have c nus in them. So I get plus, let's put a minus sign right. Just make the order right. I want the minus sign. I start with this one, which was mu, and then followed by nu. And then the other ordering comes out on the other side. So let's it makes it a commutator C nu. We know how to do commutators. They turn into curvatures. So this is R mu nu alpha nu C alpha. That's our definition from our commutator. Because one of the indices is contracted, this turns into, if I got my signs right, R minus R mu alpha, C alpha. And then I get my constraint as, let's write it as G mu alpha d squared plus R mu alpha C alpha. Okay. This determinant was the determinant of d c mu d c alpha that turns into g mu alpha d squared plus r mu alpha. So remember when we did QED, we just got box. When we did QCD, we got box plus some A term. Now we've got box, basically box plus some R term. So it's pretty much like what we did before. Then we do Fadeev-Popov that we did last time, and write this with ghost fields. So we exponentiate it and write it with ghost fields. There's going to be one ghost. There's an index alpha. So there's a ghost that carries a Lorentz index here. Okay. So the ghost field, I'll use eta mu to be the ghost field. There's basically one per constraint. We've got a constraint that carries 4 indices, so there's one for each of those guys. Okay. The ghost Lagrangian then is simply eta mu g mu alpha d bar squared plus r mu alpha eta alpha. Eta is my ghost field. Okay, so I've defined these fields. I need one for each gauge constraint, so they carry a Lorentz index, and that's it. There's the ghost Lagrangian. You add that to the rest of it. I'll summarize in just a minute. Just because I don't know a better place to do this, I'm going to give you the Feynman rule for this. Okay. Now, it must exist somewhere in the literature, but I have never seen it. So this is from my own notes. If I have a field coming in here, K index nu, this is the ghost field coming in. Here's a K prime mu going out. And here's a graviton with Q. And I have alpha beta as my indices. Okay, so I had to work this out once, so let's just give it to you. It's minus I, then it's K alpha K beta G mu nu. Okay, and that you can see is just from this first piece, the D squared. Then there's well, all right. Then there's plus Q dot K G mu alpha G nu beta plus Q mu K beta G nu alpha minus Q nu K beta G mu alpha plus Q squared G mu alpha G nu beta. And since you're so confident on my carrying the indices correctly, you'll trust this forever, I'm sure. But if you're brave and want to come up with Feynman rules, you should actually there could be an exercise if you're brave. And in fact, if you're even braver, you could try a loop with that. You do the ghost loop, which I've also done. If you've got a good table of Feynman integrals, these are massless fields. It doesn't take too much. It took me about 4 pages to do the ghost loop. Yeah, a little bit. I'm sorry. All right, so let's just summarize where we are to. So we've got our action, which is our action for the background plus something that's going to turn into the one loop effective action. Okay, so S bar is just minus 2 over kappa squared R bar with the square root of G in the integration. Okay. The extra piece, the piece that's going to turn into one loops, is e to the I. This one loop effective action is integral d h mu nu. So I can integrate over the graviton fluctuations d eta bar. So those are my path integrals. Then I have e to the I integral d4x. So I start off with the gravitational piece at second order. So let me just put it as the double bar one there. I have added gauge fixing, and I've added the ghost Lagrangian. Okay, the LG plus L gauge fixing was the piece that we wrote out. I won't write the whole thing. It's just 1/2 d bar alpha h mu nu, d bar alpha h mu nu, etc. The gauge fixing piece is this eta mu g bar mu d squared that we wrote up there. And if you look at what we've got here, this now just looks like ordinary matter loops. Okay, we can add more matter if we want. We could also add for example, you could add integral d phi e to the I integral d4x minus 1/2 phi d bar squared plus m squared minus c r bar. That's just phi. That's just the scalar matter piece. And that's sort of the same thing. Okay, but that's at this stage what it takes to have quantized. I guess I'm gonna, you know what I'm gonna do? I'm gonna stop soon. This is quantizing. Next time I come back, I'll do the one loop divergences using this Lagrangian, and then we'll move into effective field theory to get finite corrections out. The one thing I might as well end on that I copied down here is there's one of the classic endings of a paper is that of Tufts and Feldman. So they do an enormous amount of work that I haven't yet summarized yet in their paper. At the end, they say a certain exhaustion, however, prevents us from further investigation for the time being. And if you try working through it, you get a sense of why they felt that way. Okay, so there we go. A certain exhaustion, yes, but they qualify for the time being. You know, these guys are powerful. But anyhow, so when we come back, we'll do the one-loop divergences and talk about their meaning, and then move on. Okay, so we quantized today. Good.